right, I thought we would go over some of the skills on the three-quarter final review. So turn to page 8. This recording can be paused as needed to allow you to catch up and write things down. On page 8, all of these questions are about domain and range. If you remember, the domain is the x values of the function, and the range is the allowable y values of the function. So the first part here, we're supposed to determine whether each relation, each relation is a function or not. So what makes a relation what makes a relation a function is if it passes the vertical line test. So if we look at these, this relation is a function because all vertical lines only cross the graph in one location. Same with this one. The circle relation is not a function because a vertical line will pass through the graph in two locations. If you notice on the circle, this point at 2, 5 or so, and this point at 2, -5, both have the same x value but different y values. So if you notice in any of the relations above, same x value with different y values, then that relation will not be a function. So sometimes we say this has a repeated x but different y values. Okay, and just to be clear, a repeated y value is okay. So for instance, if we look at this one, this point is at 0, 0, and this point is at 4, 0. The repeated y value of 0 is okay. This is still a function. Let's review symmetry on page 9 next. Recall that when a function is even, that means it has symmetry about the y-axis. Okay, so this one here, the absolute value function, is even. It has symmetry about the y-axis. A function is odd if it has symmetry with respect to the origin. So that's rotational symmetry. An example of rotational symmetry would be in number 9. You can see that this part of the graph, when rotated 180 degrees, appears right here. So this has rotational symmetry and is an odd function. So you would want to compare all of these to see, are they even, that is symmetry about the y-axis, are they odd, that is rotational symmetry about the origin, or they may be neither. All right, turn to page 10. We're discussing maximums or minimums of a quadratic. Keep in mind that a quadratic is a parabola. So that means the maximum or minimum of a parabola is going to be its vertex. A shortcut for finding the vertex would be the x coordinate of the vertex. Let's put that vertex x equals -b over 2a. Where if we look at this function here, this is a, this is b, and this is the constant c. So the vertex x would be at -b over 2a. The vertex y you get by plugging in the x into the function. Okay, so in this question they're asking about the maximum height. That's going to be a y value. So you'll first need to find the vertex x, plug it into the function here to get the y value, and then that will be the maximum height. Looking down at the water balloon question, if we read this, it says a water balloon is catapulted into the air so that its height h in meters after t seconds is given by this or modeled by this function. How high is the balloon after 1 second? Well, for that, we're just going to plug in t equals 1 and find the h for that. For how long is the balloon more than 30 meters high? So for this is going to be your h. So you'll plug in 30 for h and solve this quadratic equation. That's going to give you two different time values. And so the difference between those times is how long. Okay, so once you get the two different time values, you'll subtract those to get the how long. Maximum height of the balloon, this is much like the first question here with the rocket. The vertex x is negative b over 2a. And then to get the height, you're going to plug that value in. Part D, when will the balloon burst as it hits the ground? Well, if it hits the ground, that's at height equals 0. So again, you're going to solve the quadratic equation here by putting in height equals 0. When you do that, you're going to have to use quadratic formula. And remember, it's a second degree equation, so you'll get two time values. I think it will be obvious which one is the time value when it hits the ground. All right, turn to page 11. This one's about parent functions and graph transformations. For each of these, 1 through 4, you're going to be determining which is the parent graph. Remember, those were the ones that used to appear on the left-hand board. So for this one, the parent graph is the quadratic y equals x squared. Okay, that'll be your parent. And then you have to determine what transformations took place. You may want to review your notes on transformations to see all of the ones that we had. In this case, the -6 after the x term would indicate that this is moved down 6. Okay, and then it says that you're supposed to graph both the parent and this function on the graph. So using two different colors, you're going to be graphing the parent, which is this one, and then the function g of x on the graph. The same thing for all of these. On page 12, we're solving polynomial inequalities. That means greater than, less than. And it says to write the solution in interval notation. I've worked out number 1, or I will work out number 1 completely here in just a moment, but it's important that you use the number line to help you solve this. It isn't the answer, but it helps you get to the answer. So to solve the inequality, you go ahead and factor. So you have the two factors here. And then you set each factor equal to the 0. So we get w equals 0 and w minus 1 equals 0. And then you have w equals 1, w equals 0. These are your boundary points. So since we had less than or equal to, these are going to be closed dots on the boundary. Okay? And then you have the boundary broken up into 3 intervals. Here's an interval less than 0, the interval between 0 and 1, and the interval that's greater than 1. And what you want to do is test a point within each interval. Okay, so I've tested -1 here by plugging it into the inequality. And then I'm asking myself as I plug this in, -1 squared minus -1, is that less than or equal to 0? So I got 1 plus 1, which is 2. Is that less than or equal to 0? My answer is no. So there will be no shading in this interval. Then I chose a point between 0 and 1, which was 0.5. That gives me 0.25 minus 0.5. Is that less than or equal to 0? So that would be -0.25, and yes, that is less than 0. So there will be shading in this interval. Okay, and then I test a point in this interval. I chose w equals 2. That gives me 2 squared. I'm plugging into here. 2 squared minus 2, is that less than or equal to 0? So 4 minus 2 is not less than or equal to 0, so there would be no shading on this interval. So the answer then, it's a closed interval including 0 and 1. And then there's your answer in interval notation. All right, let's turn to page 13 on piecewise functions. Remember with piecewise functions, we're talking about functions, 2 or 3 functions that are kind of pushed together. You want to first decide where's the boundary. Okay, so I see a boundary here at -2. This just is something to keep our eye on. It's not part of the graph, but that's the breakover where one function will be to the left of it and one function to the right. All right, if you take a look at what I've done for this piecewise function, we have the boundary at -2. Then I graphed the line here by plotting the point -2 and then plugging in the -2 to get the y value of 3. So I plotted that. It's an open dot because it's not included with this one. Okay, I then plugged in another point less than -2, so I chose -4. Plug that in, the y value is 1, so -4, 1 was my point. Create the line. The second part of the piecewise is the parabola. I went ahead and plugged in the boundary value of -2, plug that in, the y value is 3, so -2, 3. This time it's a closed dot, so that's going to become closed. Then I found the vertex by doing the -b over 2a. So if we look here, -2 over 2 times 1 gives you -1 for the x value. Plug it back in here to get the y value of 2. So -1, 2 is the vertex. A symmetric point to -2, 3 would be 0, 3. Just to double check it, I plugged in the 0 into the function and got 3 as the value. These 3 points are enough to graph the parabola, so we put it on there. Let's turn the page to slant asymptotes, page 14. The way that we find out if a function has a slant asymptote is, remember our asymptote rules. If the degree of the top is exactly 1 greater than the denominator, then you have a slant asymptote. In order to find it, you have to do polynomial division. Okay, this is the long division for example 1. I went ahead and did the polynomial division. You could also try synthetic division as well. So I got x times x minus 6 would give me x squared minus 6x. You subtract both of these. So we have x squared minus x squared is 0. And then 0x minus -6x is going to give you positive 6x. And then nothing to bring down. So back to the top, what times x is 6x? That's where I get my 6. So this has to be 6x. And then 6 times -6 would be minus 36. Remember, we're subtracting this line. So I put negative and then parentheses. 6x minus 6x is 0x. 0 minus -36 is positive 36. This is your remainder. It doesn't matter anyway. So up here, we get the slant asymptote. So that's going to be a linear equation, y equals x plus 6. Okay, let's flip to page 15. This one's talking about roots and zeros, which for practical purposes are the same thing. If we look at the first example, though, it's a quadratic equation, so it will have 2 roots. All of these are quadratic equations, so they'll all have 2 roots. But how many zeros would be how many x-intercepts? So in this case, this just has 1 0. It's a repeated root. It has 2 roots at, let's see, it looks like x equals 3 are the 2 roots, but they're repeated, so it's 1 0. This one, notice that the axis is up here, so the parabola opens down below the axis. It has no x-intercepts. So 2 roots and no zeros. Zeros would be actually imaginary. And then here we've got 2 real roots, but yeah, and then also 2 zeros as well. Okay, for this, okay, we're looking at the polynomial function. The degree is 5, so the maximum number of complex roots or zeros is 5. How many positive roots is Descartes' rule of sign changes? So I see 1, 2, so 2 or 0 positive real roots. For negative real roots, you would have to plug in your f of negative x and count sign changes. Factors of p and q, remember the 12 is p, the q is 3. And then the p over q, factors of 12 over factors of 3, will give you the possible rational roots. Remember, those become your choices for trial and error of synthetic division. Let's look at page 16, exponential growth and decay. Most of these problems can be done using this equation. This represents final amount. This represents initial amount. A naught would be initial amount. R is the rate, so this is either the growth rate or the decay rate. Notice that with a growth rate, the rate will be larger than 1, so 1 point something. With a decay rate, then it'll be a decimal value, let's say 0.75, less than 1. T is time, so it could be days or years depending on the problem. For example 1, I started to do this problem. The growth factor for the world population would be your 1.26, or the 2.26 is the growth. 1.26 is going to be your rate. Write a model is write an equation, so this would be your example or your answer for part B. Part C says let x be the number of years past the year 2000, so we would want to change this t to an x, I suppose, and then find the world population in 2010. So that would mean 10 years past 2000, you'd be putting in 10 here for the exponent and solving that. This same kind of model can be used for all these. If you look down here at number 3, the population decreases. So anytime this decreases, you should have a growth rate, which is actually a decay rate. So if it decreases at 3.5% per year, you're doing 100% minus 3.5%. Okay. Okay, so this gives you 96.5%, which is a growth factor of 0.965. So that's actually decay, because when you multiply it times a number, you're only going to return 96.5% of that number. All right, just as a reminder, these pages are all due by Friday. This video will be uploaded to the YouTube channel on my website, so you can go there to find that and watch any of these again as you need to.